Welcome to today's video. Today we'll be talking about convex functions and convex sets. Now, the motivation for this comes from the KKT theorem. You will remember that KKT is used to find optima of constraint optimization problems. And the one problem here is that KKT provides a necessary but not a sufficient condition. So every optimum has to be a KKT point under certain conditions. But not every KKT point is necessarily an optimum. And with convexity, we'd like to identify a setting, situation for the objective function and for the constraints where KKT is actually also sufficient. So if we can find a KKT point in such a constraint setting, then we can be sure that it is actually an optimum. And it turns out convexity provides the right framework for this. So the problem is KKT is a necessary condition, but it's not sufficient for optimality. So what we'd like to do is we'd like to identify a setting where KKT is also sufficient. And that is just what convexity will provide. So let's first define what we mean by a convex function and a convex set. Let's start with the sets. So point one, the set will take a set X subset of R to the n as usual. And we'll call that set convex if it contains, for any 2 points in the set, the complete line segment connecting those 2 points. So whenever I pick 2 points in the set, I draw the line between them. This whole line needs to be contained in the set. Okay, let's first define that. So it's called convex if for any 2 points x and y in capital X, the line segment connecting x and y is also contained in X. Or more formally, the line segment that is the following set. So we can write this as lambda times x plus 1 minus lambda times y, where lambda is a parameter between 0 and 1. This is the line segment, and that has to be contained in X. Right? Now you notice here, if we set lambda to 0, then this expression here becomes 0 times x plus 1 times y, so it's just y. If we set lambda to 1, then this becomes x plus 0 times y. And for any other value of lambda between 0 and 1, we get a little bit of x, a little bit of y, more of one, less of the other. So we are kind of going through all possible combinations of x and y that are in between those 2 points, right? So that is exactly the line connecting x and y. And by the way, this here, this is also called the set of convex combinations of the points x and y. Yeah, so almost the same thing as a linear combination, with two constraints. First is all the parameters are between 0 and 1. And the second is the parameters always sum up to 1. So if we just have two variables here, two parameters that sum up to 1, then of course we can say that's just one parameter and the other is then 1 minus lambda. That's what we're doing here. Okay, so that's a convex combination, but we don't really want that. We don't really need that. Okay, quick example. How does that look like? What does that mean geometrically? Well, let's consider a set. It looks like this here. Then this is a convex set, because if you choose any 2 points in that set, like these two, for example, this is x, this is y, and then we're looking at the line connecting those two, this line is completely contained in the set. And that is true for any 2 points that I could choose. So this is clearly a convex set. What does a non-convex set look like? Well, here's an example. So this is a non-convex set. Of course, there are points in that set where the segment connecting those is contained in the set, but there are also point pairs in that set where the line connecting those two is not contained in the set. And here are two such points. Let's take this and this one. Yeah, so that is x, that is y. And the line connecting those two is this one here, right? And that is clearly not contained in the set. It contains points that are not lying in the set. So this is a non-convex set. So geometrically, convexity means something like roundedness, right? So it's rounded in a way such that no line connecting any 2 points is outside or partially outside of that set. Okay, so that's a convex set. Let's see what a convex function is. Again, we want to set x in R to the n, and for a convex function, we want a domain that is already convex. We'll need that for the definition. So we'll have a set x in R to the n that is convex. And then we'll take a function, so a function f defined on that set and mapping to the reals. So we can only use real numbers for that, and we'll see why in a minute. Such a function is called convex, or even strictly convex. If for all lambda in the interval 0, 1 and all xy in the set x, the following holds. The function value at the point lambda x plus 1 minus lambda y. So we're taking the convex combination of x and y, an arbitrary convex combination, and that is why the set x needs to be convex, to make sure that this convex combination is always contained in the set x. And we want that to be strictly less or equal to lambda f of x plus 1 minus lambda f of y. And we want strict inequality if we have a strictly convex function. Again, let's have a look at what that means geometrically. So let's say we have a function like this is our coordinate system. And let's say we have a convex function in that coordinate system. And we're looking at 2 points, 2 points on the domain. So for example, here's a point x, here's a point y. Then we have to compare the value of a convex combination of x and y to the convex combination of the function values f of x and f of y. So let's mark those function values first. Now if we go up here, there, this is f of x. And going up here, here that is f of y. And we also have a point somewhere in the middle, right? So somewhere in there, like for example, let's take this point here, right? So that is our convex combination here, lambda x plus 1 minus lambda y. An arbitrary point between x and y, actually. And of course, we also need to have a look at the function value of that point. Right, so this is the value of f of lambda x plus 1 minus lambda y. This here. Yeah, so that is the left-hand side. And what it says is the condition, this point is lower or equal to the convex combination of those 2 points corresponding to this. So the convex combination of those 2 points, basically that corresponds to the line that connects those 2 points. So something like this, yeah? So that's the convex combination of those two. And the corresponding point here is this one. So this is lambda f of x plus 1 minus lambda f of y. And the condition says this point is this point here that is above this point. And that's true for every point that we can choose between x and y. So in other words, well, the exact function values always lie on this line here. In other words, what that means is the line connecting f and x and f of y always lies above the function graph. Okay, so that's convexity for a function. Okay, so what that means is the function value between x and y is below the line connecting those 2 points, or the points f of x, f of y. Yeah, or in other words, on the graph, the line connecting those 2 points, or any 2 points on the graph, is always above the graph. Yeah, so a line connecting any 2 points on the graph of f is always above the graph. Okay, so this is an example for a convex function. Let's see quickly an example for a non-convex function as well. It's not easy to see. So a non-convex function, for example, might be a function looking like this. Right? This is obviously a non-convex function because, for example, if we choose this and this point here, then the line connecting those 2 points is below the graph. Okay? So that function is non-convex. Okay, and finally, one more thing that we want to define. There's also the notion of a concave function, just to round this off. And a concave function is basically a convex function flipped around. So minus the function is convex. So a function f x to r on a convex set x subset of r to the n is called concave if minus f is convex. So the function that we've seen here above, this one, that is a concave function, because minus that function would then be convex. Okay, so that's the definition of convex sets and convex functions. Before we move on to connecting this notion with the KKT, let's have a quick look at how we can find out if a differentiable function is convex or concave. And as you can imagine, there is an easy criterion here, similar to what you know from one-dimensional analysis, and it relates to definiteness of the Hessian once again. Okay, so let's formulate that as a theorem. So we want x to be open and convex. So let x be a subset of r to the n, be open and convex, and let f be a function that is twice continuously differentiable on x, so in C2 x. Then the function is convex if and only if the Hessian is positive semi-definite for all x in the domain. The function f is convex if and only if hf of x is positive semi-definite for all x in the domain, capital X. And second, if the Hessian is even positive definite, not just semi, but positive definite, then f is even strictly convex. So if hf of x is positive definite for all x in X, then f is strictly convex. And to round this off, a very quick example of the difference between a convex and a strictly convex function. Actually, the functions that we have seen so far are all strictly convex, so here again, that would be a strictly convex function. And in contrast to that, a function that is not strictly convex but still convex, that could look, for example, that could look like this. Right, so that is convex but not strictly convex, because here, if you take these 2 points, for example, then the line between those two is exactly equal to the graph. It's not strictly above the graph, it's exactly equal to the graph. And that's why this is a convex function, but not a strictly convex one. Okay, so this concludes the introduction of convexity. In one of the next videos, we'll then see how this relates to the Karosh-Kuhn-Tucker theorem. I'll see you then.